Let us discuss about the lasers. The word laser, the acronym laser, stands for light amplification by stimulated emission of radiation. The first working laser was designed by Theodore Maiman in the year 1960 at Hugg's Research Laboratory. The main principle behind the working of laser is population inversion and stimulated emission. So these are the three principles. So these are the two principles on which the laser works. One is population inversion and the other is stimulated emission. And this laser is an optical device having the following properties. The source, or in other words, light emitted from the laser, light emitted from the laser device is highly monochromatic. It will have very high intensity. The coherence of laser light is very large, and laser light will be highly direct. There will be negligibly small deviations, and these properties, along with population inversion and stimulated emissions, will be discussed in detail later. For the light to be amplified in a lasing device, the lasing device should have a medium called active medium. If there should be an active medium in the lasing device for the light to be amplified, because the amplitude of laser light is very large. As the amplitude is large, the intensity will be large. So we are now studying the interaction of electromagnetic radiation with atomic energy levels. The electromagnetic radiation, when falls on the atomic energy levels, there will be an interaction between the atoms of the atomic energy level and the incident electromagnetic radiation. For this to study in detail, we are considering two energy level systems. One is the ground level or the ground state, and the other is the higher level or the excited state. Ground level, let the ground level will have an energy E1 and the excited state will have an energy E2. The lower level will have an energy E1, the higher level will have an energy E2. When an atom in the ground state absorbs the energy of a photon, it gets excited, and the process is called stimulated absorption or simply absorption. Simply absorption. So for this to understand in detail, we are considering a photon of energy h nu, where h is Planck's constant, nu is the frequency of the incident radiation, h nu, let h nu will be equal to the energy difference of two levels under consideration. That is h nu equals E2 minus E1. If such a photon is incident on this energy level or this system, the probability of absorption or the probability of interaction of this photon is more with the atoms in the ground state, because there are more number of atoms in the ground when compared to that in the excited state. If one of the atom in the ground state absorbs this energy of the photon, then that particular atom will rise to the higher energy level, and that is represented over here. Here represents the atom which is in the ground state. When this atom gets interacted with the photon of energy h nu, it moves to the excited state. A represents the atom in ground state, A star represents atom in the excited state. Therefore, star represents excited state or the higher energy level. The number of such transitions or number of such atoms which are moving from the ground state to the excited state or from lower energy level to the higher energy level due to the absorption of photons of energy or due to the interaction of or due to the interaction with the electromagnetic radiation depends on the number of atoms present in the lower energy level, depends on number of atoms present in the lower energy level, and it also depends on number of photons interacted with the atoms. Number of upward transitions, number of upward transitions or number of transitions of atoms from lower energy level to higher energy level depends on the number of atoms present in the lower energy level, that is N1, and also depends on the number of photons interacted with those atoms. And therefore, NAB, N represents the number, AB represents the absorption. In the sense, number of absorption transitions is represented by NAB, that is equal to B12 N1 rho V delta T, where B12 is the probability of absorption transition, probability of absorption transition. Therefore, B represents stimulated transition. Stimulated transition. 1 2 represents absorption transition. 1 2 represents absorption or the process of transition from lower to higher, from energy level 1 to energy level 2. Therefore, B represents the probability of stimulated absorption or the stimulated transition from level 1 to level 2, or the probability of upward transition. Rho represents the energy density of the incident beam per unit volume of incident radiation. N1 represents the number of atoms in the lower energy level E1. Delta T represents the time during which these upward transitions takes place. The second probability of interaction is when the atoms gets interacted with the photons of energy or the atoms gets interacted with the incident radiation. The second possibility will be spontaneous emission. Spontaneous emission. If we consider more number of atoms in the excited state than in the ground state, or in other words, in the previous case, there was only upward transitions due to absorption of incident radiation. When the atoms move to the excited state or the higher energy level, those atoms will be unstable in the higher energy level. Therefore, they seek the stability, they seek to occupy the stable state. Therefore, within about 10 power minus 8 seconds, or this will be equal to 10 nanoseconds. So within this time, they decay back to its ground state on its own, and this is called the spontaneous emission. They return back to the ground state by themselves without any stimulation. Therefore, it is termed as spontaneous emission. Spontaneous emission. So here it is represented in detail. In 10 power minus 8 seconds, these atoms return back to ground state. While it is returning back to ground state, the energy difference will be emitted in the form of photon of energy h nu. That is equal to E2 minus E1. When an atom from excited state returns back to ground state on its own, it is called spontaneous emission. During the process, The energy difference E2 minus E1 that will be equal to h nu will be emitted in the form of photon. Will be emitted in the form of photon. Here it is represented. A star, that is atom which is in excited state, return back to ground state with the liberation of h nu amount of energy, that is nothing but a photon. Due to this spontaneous emission, photons will be emitted in all possible directions and therefore they are incoherent. If they are emitted in a particular direction and if they are emitted together, then we say that it is coherent. As they are moving randomly in all directions, they are said to be incoherent. And the number of such spontaneous transitions depends on the number of atoms present in the excited state. Number of atoms present in the excited state. And let it be N2. Therefore, NSP represents the number of spontaneous transitions. In other words, number of downward transitions or number of transitions from higher energy level to lower energy level, that will be equal to A21 N2 delta T. A represents spontaneous, A represents spontaneous, B represents stimulated. Remember it. 2-1 represents the transition from the second level to the first level, or from excited state to ground state, or from higher level to lower level. N2 represents the number of atoms in the higher energy level, and delta T represents the time during which the number of atoms undergoing downward transitions. This is about spontaneous emission. There is one more possibility when an atom interacts with electromagnetic radiation, and that is nothing but stimulated emission. Nothing but stimulated emission. If a photon of energy h nu equals E2 minus E1 interact with the atoms in the excited state, since there are more number of atoms in the excited state, the possibility of interaction of this electromagnetic radiation is more with the atoms which are in the excited state. If such an interaction takes place, this photon stimulates this photon stimulates the atom which is in the excited state to return back to the ground state. And this process is called stimulated emission. This photon interacting with the atom in the excited state, it makes the atom to return back to ground state, and hence the name stimulated emission. Stimulated emission. Photon is stimulating the atom in the excited state to return back to ground state, therefore called stimulated emission. During the process, during the process of stimulated emission, when an atom makes a transition from higher energy level to lower energy level due to the stimulation of the interaction of electromagnetic radiation or a photon, two identical photons will be emitted. Two identical photons will be emitted. They are identical in the sense they are coherent and and further further they have same phase, same direction of propagation, and same polarization, same direction of propagation, same phase, same energy. So these two photons are called identical photons. They are identical and therefore they are coherent. And this is termed as stimulated emission. During stimulated emission, a atom in the excited state interact with a photon of energy h nu, and hence the atom return back to ground state with the liberation of two photons of same properties, same characteristics. And the number of stimulated emissions depends on the number of atoms present in the excited state. It depends on the number of atoms present in higher energy level. It also depends on the number of photons incident, the number of photons interacted with atoms in the higher energy level. Therefore, NST equals where NST represents the number of stimulated transitions. Number of stimulated transitions that will be equal to B21 N2 rho V delta T. B21 is the probability of stimulated transition. B represents stimulated. 2 1 represents emission. 1 2 represents absorption, that is from lower to higher. 2 1 represents emission, that is from higher to lower. B represents stimulated. Therefore, B12 is the probability of stimulated emission. N2 represents the number of atoms in the higher energy level. Rho V represents the energy density of incident radiation per unit volume. Delta T represents the time during which the stimulated transitions takes place. This is about the stimulated emission of electromagnetic radiation.